Hello and welcome to MH1801 Tutorial 5. In this tutorial we'll be focusing on second order linear differential equations that also have the property of being non-homogeneous. In particular, we're going to look at differential equations of this particular form. On the left hand side, you see we have what we encountered in the previous tutorial. We have our derivatives up to the second order, and they are multiplied to constants. So a, b, c are constants, and the thing of difference here is that gx is supposed to be a non-zero function. To solve these differential equations, we're going to make use of the method of undetermined coefficients. How do we use it? The first thing to do is to take out the left hand side and solve the corresponding complementary equation. This is our complementary equation. We'll take the left hand side and set it to 0. And using the key theorem from the previous tutorial, this will give us a general solution yc. C indicates this is the complementary solution. After we are done with this part, what we need to do is to find a particular solution. This will usually involve making a so-called clever guess for just such a solution, yp. And in doing so, we may encounter some undetermined coefficients as well. The most important thing to note is that yp should satisfy the original differential equation star. That is to say, when we plug in yp into this equation, that is, substitute yp for y, the derivative yp prime for dy dx, and yp double prime for the second order derivative, the left hand side should be precisely g of x. That is what we mean by a particular solution. So that is what we need. We have to compute the first order derivative and second order derivative of yp and substitute them into our differential equation star. And in the process, we also need to try to solve for the undetermined coefficients, because that would help us to find out a particular solution. We cannot have undetermined coefficients in our particular solution, so they have to be eliminated. In the process, we need to solve for these coefficients. The only place where we should have arbitrary constants is in yc. yc is the only place where we should see arbitrary constants appearing, just as you would have in the key theorem. Here are some points to take note of. So once we have yc and yp, then we can immediately write out the general solution to our differential equation star. It is simply y equals to yc plus yp. And we don't have to do anything else. We can leave it in this form. However, we understand that there isn't any straightforward way to get a perfect guess to obtain yp. Sometimes we may not know how to do it. But in this tutorial, we're going to examine various ways to obtain yp using some sensible observations to help us make a good guess. This will involve looking at how gx is defined. For example, if gx is a polynomial of degree n, then by taking successive derivatives, the degree of the derivative is going to decrease. That is, or to say it another way, this is a polynomial. The kth order derivative of a polynomial is always a polynomial. And moreover, the degree of the successive derivatives will be decreasing, increase the value of k. Of course, at some point, we would have eliminated all the non-trivial terms, and at some point, the corresponding derivative would just be 0. So that is something we should take note of here. Additionally, let us suppose that g of x is defined in terms of an exponential function, e to the power of fx. Then, by looking at what happens when we take derivatives, we will see that we end up producing e to the fx in every one of our derivatives. That is to say, no matter how many times we take the derivative, e to the fx is always going to appear inside of, say, the kth order derivative. If it turns out that g of x is a trigonometric function, such as sine x or cosine x, then we can see that by looking at what happens when we take successive derivatives, g of x alternates between sine and cosine. If we start with sine x, we would switch to cosine x, and then on the next derivative, it would become minus sine x. Similarly, for g of x equals to cosine of x, we would switch from cosine x to minus sine x, and then in the next derivative, we will get minus cosine x. That is what we mean, that the derivatives will alternate between cosine x and sine x. As a consequence of this, if we were to take the function f of x equals to a constant, times sine x plus b times cosine x, then no matter how many times we take the derivative of this function, it will always be a sum of a sine function and a cosine function multiplied to by certain constants for which we can solve. There are also these standard rules of differentiation that we should keep in mind. The addition rule, the product rule, quotient rule, and chain rule. If we have, for example, a sum of two functions, by the addition rule, it follows that the kth order derivative is a sum of two kth order derivatives. We just need to differentiate f of x and g of x k times, and that will give us the kth order derivative of g, large G. If we have a product of two functions, fx times g of x, the product rule tells us it is going to become a sum of derivatives, and every term inside of our kth order derivative is going to involve one of the derivatives of f and also one of the derivatives of g up to a certain order for k1 and k2. You can see this immediately from the formula for the product rule. When we do the product rule, we have to differentiate f of x and multiply it to g. Then we add on f of x multiplied to the derivative of g. So just repeating the product rule on such an expression will allow us to draw such a conclusion regarding the expression for any kth order derivative of the function g. It should have this form. It's a sum of terms of derivatives of f and g. Of course, you can also think about what happens in the case of the quotient rule and the chain rule. In this tutorial, we won't need to deal with these two situations involving the quotient rule and the chain rule. But an important thing to note is that our differential equation is of order 2. Therefore, we just need to calculate derivatives up to the second order. We don't need to go any further than that. And therefore, for all our observations that we make, we just need to make them up to the second order derivative. There's no need to go beyond that. And when we are looking at g of x, in order to construct yp, we should be asking the question, how should yp be constructed in order to give g of x when we differentiate yp 2 times up to order 2 and substitute back into our differential equation? So the key things to note is that we just need to stop at order 2, and we should be thinking about what happens when we substitute yp into our expression in star to produce on the right hand side g of x. These will help us to formulate good choices for a particular solution yp, and it will help us to solve the questions in this tutorial.